Welcome to The Explainer. Today we're heading to the freezing edge of West Antarctica to talk about a literal giant. We are going to unpack the mechanics of the Thwaites Glacier, a structure so incredibly vast that its shifting ice is fundamentally changing global coastlines as we speak. So let's dive right into this and see exactly what the data tells us.
Now, you've probably heard Thwaites referred to by a rather dramatic nickname. Back in a May 2017 article for Rolling Stone, journalist Jeff Goodall called it the Doomsday Glacier. And man, that moniker caught on like wildfire in the global media. The media loves this name, obviously, because it captures the sheer, massive scale of the global stakes involved here. But it's really important to note that this nickname is actually pretty controversial among scientists. A lot of leading glaciologists prefer to avoid that kind of apocalyptic language entirely. They just want to focus strictly on the structural data and the physical mechanics of the ice itself. And honestly, that objective, data-driven approach is exactly what we're going to be taking today.
Here is our roadmap for today's explainer. First, the so-called Doomsday Glacier. Second, the mechanics of a collapse. Third, volcanoes and hidden canals. Fourth, rising global sea levels. And finally, predicted timelines in the future.
Okay, Section 1. The so-called Doomsday Glacier. What and where exactly is this thing?
The sheer physical footprint we're talking about here is just staggering. At 120 kilometers wide, Thwaites is the single widest glacier in the world. It covers an area of roughly 192,000 square kilometers. To put that into perspective, if you look at the state of Florida, which sits at about 170,000 square kilometers, this glacier is literally bigger than the entire state. It's just a massive, mind-boggling amount of frozen mass, with the ice thickness actually measuring up to 1,200 meters straight down from the surface to the bedrock.
But despite its immense size, humanity has only recently gotten a clear look at it. The coastline was actually first officially sighted during Richard E. Byrd's third Antarctic expedition in 1940. Just a few years later, in 1947, 65,000 aerial photographs from Operation High Jump finally allowed us to formally map the glacier's tongue. And it wasn't even officially named until 1967, after Friedrich T. Thwaites, a really renowned glacial geologist who, ironically enough, never actually set foot on the glacier himself. Moving on to Section 2, Mechanics of a Collapse. Let's look at how a giant like this actually breaks down.
You absolutely cannot understand Thwaites without understanding this one key term, the grounding line. This is the exact critical boundary where the heavy glacier ice detaches from the solid continental bedrock and actually starts floating on the ocean water. And this is the glacier's primary weak point. Because the bedrock beneath Thwaites actually slopes downward the further inland you go, warm ocean water can creep right underneath this line, melting the glacier from the bottom up and forcing that grounding line to retreat further and further back.
And this brings us to a really crucial process known as marine ice cliff instability. Think of it as a three-step chain reaction. First, as we just discussed, that warm water undercuts the ice at the grounding line. Second, this weakening seriously threatens the floating ice shelf out in front, which is basically the structural brace that physically restrains the rest of the glacier behind it. If that bracing ice shelf collapses, we hit step 3. The remaining edge of the glacier turns into these unsustainably tall, completely exposed ice cliffs. Without the ice shelf there to hold them back, these massive cliffs become structurally unsound and they fail, shedding huge icebergs directly into the ocean. This whole process is exactly why, since the 1980s, scientists have referred to Thwaites as the weak underbelly of the West Antarctic ice sheet. Think of Thwaites like a giant cork in a bottle. Because of its massive width and its really strategic location, it physically holds back the vast ice reserves sitting behind it in the center of the continent. If the Thwaites cork pops or collapses, the structural integrity of the entire West Antarctic ice sheet is completely compromised. That would eventually allow all of that inland ice to just flow freely right into the sea.
Let's jump into Section 3, Volcanoes and Hidden Canals. We're heading into the subglacial world.
There is this wild duality to Thwaites. Up on the surface, everything appears as a freezing, massive, static expanse of white. But the underworld of Thwaites? It's shockingly dynamic. Beneath thousands of feet of ice, you have active geothermal heat, subglacial volcanoes, and this incredibly vast network of fluid swamp canals and streams. The interaction between this warm, active bed and the frozen ice above plays a massive role in dictating exactly how fast the glacier flows towards the sea.
Recent expeditions have really pulled back the curtain on this subglacial world. And honestly, the discoveries are absolutely staggering. Scientists have mapped 138 volcanoes right beneath the West Antarctic ice sheet. They found geothermal hotspots generating a heat flow about 3.5 times higher than the global average. And get this, in 2019, NASA researchers discovered an underwater cavity carved into the underside of the ice that is nearly 350 meters tall. That's an empty space roughly 2/3 the size of Manhattan, and it formed mostly in just 3 years simply from melting ice.
Section 4, Rising Global Sea Levels. Let's zoom out and look at the global coastline impact.
So, between 1992 and 2017, Thwaites experienced a net loss of over 600 billion tons of ice. Let that number sink in. Right now, today, the water pouring off this single glacier currently accounts for 4% of total global sea level rise. That is a massive, massive contribution coming from just one single geographic feature.
But the real looming concern is what happens if the whole thing goes. If the entire volume of Thwaites Glacier were to melt, which is a process expected to take place over multiple centuries, it would add 65 centimeters, or just over 25.5 inches, to the global sea level. To put that into perspective for you, that single event would be more than twice the total sea level rise the entire planet experienced between the years 1901 and 2018.
Finally, Section 5, Predicted Timelines and Future. Let's look at what the models tell us is next.
Looking strictly at the numbers, in the near term, researchers estimate that the eastern ice shelf, that floating brace we talked about earlier, could collapse as soon as the 2030s. That alone would bump Thwaites' contribution to sea level rise up to 5%. If we stretch out to a 100-year timeline of gradual retreat, we can expect an additional 14 to 42 millimeters of sea level rise. But the most alarming models suggest that somewhere in the 200 to 900-year window, the glacier reaches a tipping point of rapid, irreversible collapse. That would add over 1 millimeter to the global sea level every single year until it is entirely gone.
Faced with this kind of timeline, some researchers are proposing some seriously radical interventions. One of the most prominent geoengineering ideas out there right now is the installation of underwater curtains. Basically, these would be massive sheets of flexible material anchored directly to the seafloor of the Amundsen Sea. At 80 kilometers long and placed at a depth of 600 meters, these curtains would physically block those warm ocean currents from ever reaching the glacier's grounding line. It is a completely unprecedented concept, estimated to take a decade to construct and costing up to $80 billion.
Which leaves us with this final thought. We now understand the anatomy of this giant. We know exactly how warm water undercuts its grounding line. We know the incredible threats lurking in its geothermal underworld, and we know exactly what a collapse means for our global coastlines. But as we face all of this data head-on, we really have to ask, is human engineering on a scale never before attempted actually enough to outmaneuver the incredible forces of nature and stabilize the Earth's most critical glacier? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll catch you next time.